Let's begin the new section, 3.2. In this section, we're going to learn about norm, dot product, and the distance in Rn. So norm is basically the length. So when we say the norm of a vector, we mean the length of that vector. And dot product is an operation which is defined between two vectors. We can multiply two vectors using this operation. And distance, you have a pretty clear idea about distance of 2 points in, for example, R2 or R3, because you can visualize them. But we can also define distance in Rn. So this is pretty much the topic of this section: norm, dot product, and distance in Rn. So norm of a vector v is the length denoted by this symbol. So we're using double vertical bars, and whenever you see this, it's norm of the vector v, and by that we simply means how long the vector v is. So if this is vector v, norm of v simply means the length of that vector. And you can see that if I put that vector v in the standard position, then the initial point is at 0, 0, the origin. The terminal point is going to be here at the point v1, v2. So v1 and v2 are the components of the vector. And then you can see it's simply the Pythagorean theorem, because the vector is going to be the hypotenuse of this triangle here, right triangle here. And the length of the hypotenuse is going to be root v1 squared plus v2 squared. It's basically the Pythagorean theorem that c squared is a squared plus b squared. So c is going to be root a squared plus b squared. So in this case, v1 and v2 are a and b, and c would be the norm or the length of the vector. Now in R3, it can also be proved that the vector in R3, the norm of the vector, if v is v1, v2, v3, a vector from R3, the norm of that is going to be root v1 squared plus v2 squared plus v3 squared, which is going to be very similar to this one. So you just have an extra component, v3. And it's very easy to prove, because you can think of this as, you can think of the length of v in the 3 space as the hypotenuse of this triangle here. Yes, we have a triangle here, and the norm of v would be the length of the hypotenuse of that triangle. Now, one of the sides of that triangle here is basically the hypotenuse of another right triangle, the one that's here. Yes, so think of AB as the hypotenuse of this triangle here, and the length of AB is simply going to be v1 squared, which is the length of this, plus v2 squared, which is this length here, square rooted. So that would be the length of AB. Now, in order to get the length of the vector here, we're going to say it's the square root of the length of AB plus squared plus v3 squared. So it's going to be, this part here is the length of AB squared plus v3 squared. And since square root and raising to power of 2 cancel out, we get this formula here. And now you can see a natural generalization of that for Rn would be this definition here. If vector v is a vector from Rn, so it has n components, v1, v2, all the way to vn, then the norm of v, also called the length or the magnitude of v, is denoted by v between 2 double vertical bars, is going to be defined like this. v1 squared plus v2 squared plus v3 squared all the way to vn squared, and then you add them all up and you take the square root of the sum. Any questions so far? Example 1, calculate norm of these two vectors. So I'm going to do one of them for you and let you do the other one on your own. So if v is -3, 2, 1, then the norm of v, according to this formula, is going to be square root of the first component squared plus the second component squared plus the third component squared. So it's going to be 9, 10, 14, root 14. Okay, so now that we defined norm, let's look at some properties of norm. If v is a vector in Rn and k is any scalar, so k could be any scalar, positive, negative, 0, any real number, then part A of the theorem says that norm of v is greater than or equal to 0. This basically comes directly from the definition. If you look at the definition here, norm of v is the square root of some non-negative value. Yes, so the square root of some non-negative value is definitely non-negative. And then part B says that if the norm of v is 0, that's only possible if all the components of v is 0. So if v is, for example, v1, v2, v3, and norm of v is 0, that means square root of v1 squared plus v2 squared plus v3 squared is 0. That means v1 squared plus v2 squared plus v3 squared is 0. That would only be possible if all of them are zeros. Yes, because if any of these three components is not 0, then when you raise it to power of 2, you're going to get a positive number, and then this cannot be 0. So this implies that v is actually the origin, 0, 0, 0. And part C can be proved doing some simple algebra. If you have norm of k times v, that's going to be absolute value of k times norm of v. So we know that kv is defined to be like this. It's k times v1, v2, v3. So it's kv1, and the second component is going to be kv2, and the third component is kv3. So norm of this is going to be the first component squared plus the second component squared plus the third component squared all the way to the end. Now you can see that k squared can be factored out. So there is a k squared here. For every term there is a k squared, which can be factored out. And we know what root k squared is. That's going to be absolute value of k. And what remains as the second factor is going to be norm of v. Are we good? Any questions? Okay. So a vector of norm 1 or a vector of length 1 is naturally called a unit vector. So if v is any non-zero vector in Rn, then we can prove that for any vector v, member of Rn, we can prove that the vector u, which is defined to be 1 over norm of v times v, is going to be a unit vector that is pointing towards the same direction as v. This is called normalizing a vector. So for example, you have a vector v, yes, and imagine this vector is of length, let's say 4, 1, 2, 3, 4. So imagine it's 4 units of length, and then you can easily find u, which is a vector of the same direction but of length only 1. using this formula. Just need to divide v by the norm of v, or multiply v by 1 over norm of v. That will give you the unit vector. So if v is any non-zero vector in Rn, then u, which is defined like this, 1 over norm of v times v, is a unit vector that points in the same direction as v. The process of multiplying a non-zero vector v by the reciprocal, or 1 over, of its length to obtain a unit vector is called normalizing v. So you're creating a vector of unit 1. So if I say normalize this vector, it simply means find a vector that has the same direction as this one, but it is of length 1. So if v is 2, 2 minus 1, you can see that norm of v is going to be root 2 squared plus 2 squared plus 1 squared. That's going to be 5. Yes? No. 4, 4. It's going to be 9. Yeah, because 2 squared is 4, 2 squared is 4, negative 1 squared is 1, 4 plus 1 is 9. So that unit vector is going to be 1 over root 9, which is 3, times 2, 2 minus 1. So it's going to be 2 over 3, 2 over 3, and minus 1 over 3. Now imagine I ask you find a vector of length 2 in the same direction as v. If I say find a vector of length 2 in the same direction as v, then since this one is a vector of length 1 in the same direction as v, I would just need to multiply this by 2. So 2u would be a vector of length 2 in the same direction as v. If I say find a vector that has the opposite direction as v of length 1, that vector would be minus u. If I say find a vector that has the opposite direction as v and it has length 5, the answer would be minus 5u. Does that make sense? Any questions?
Would you mind re-explaining that, please?
Yes. So u is a vector like this. It's a vector, if this is v, then u is going to be a vector that points towards the same direction. It's parallel to v, and the length of u is going to be 1. Okay. Now, if I want to have a vector in the same direction as v, but of length 2, that vector would be 2u. Yes, it's going to be this. 2u. And if I want a vector that is of length 1, but points towards the opposite direction as v, that would be minus u.
Okay, got it. Thank you.
Sure. Okay, so what are standard unit vectors? In R2, there are 2 standard unit vectors. We call them I and j. I is the vector 1, 0, and j is the vector 0, 1. So if this is the R2, and these are, let's say, this is, for example, 1, this is 2, negative 1 here, negative 1 here, 1, 2. So this vector here and this vector here. If this is the x-axis, that would be I. And if this is the y-axis, that would be j. These are called standard unit vectors. In R3, the standard unit vectors are I, j, and k. I is 1, 0, 0. J is 0, 1, 0. And k is 0, 0, 1. So these are very similar to the rows of the identity matrix. Actually, the first row of the identity matrix is I, the second row is j, and the third row is k. because of the way we define vector algebra, the way we define vector addition and scalar multiplication, it is possible to write any vector as a linear combination of these standard unit vectors. So any vector in R2 can be written as a linear combination of I and j. For example, if I have the vector 2, 3, I can write as 2i plus 3j. And you see it works because 2, 1, 0 plus 3, 0, 1. That's going to be 2, 0 plus 0, 3. And if you add them up, you get 2, 3. And same works for any vector in R3 or generally any vector in Rn. So for example, this vector here, negative 3, 2, 1, which is a vector from R3, can be written as negative 3i plus 2j plus 1k. It has to be plus 1k. That's a mistake here because that's a positive 1. So it has to be plus k. Make sense? So generally for any vector, and here I'm giving an example from R3, I can write that as v1i plus v2j plus v3k, where these vectors I, j, k are the standard unit vectors. Okay, now it's very easy to define the distance between 2 points. For any 2 points P and Q, it could be in R2, it could be in R3, it could be in Rn. We can define the distance between these 2 points to be the length of the vector PQ. So the norm of the vector PQ would be the distance between the points P and Q. If P and Q are points in R2 or R3, and since norm is also defined for Rn, this can be generalized to Rn, then the length of the vector PQ is equal to the distance between the 2 points. By generalizing this idea to Rn, we have if P is this point from Rn and Q is this point from Rn, then these 2 points, the distance between these 2 points in Rn is simply the norm of the vector PQ. So we know that if this is x1, x2, all the way to xn, and this is y1, y2, all the way to yn, then the vector PQ is going to be defined as terminal minus initial. So it will be a vector like this: y1 minus x1, y2 minus x2, all the way to yn minus xn. Now, what is the norm of this vector, which is the distance between P and Q? It's going to be this component squared plus this component squared all the way to this one is squared, and then finally square rooted. So y1 minus x1 squared all the way to yn minus xn squared, and then a square rooted. That would be the distance between P and Q. So if I ask you to find the distance between these 2 points in R4, P is 1, 3, negative 2, 7, and Q is 0, 7, 2, 2. Then the vector PQ is going to be terminal minus initial. So 0 minus 1 minus 1, 7 minus 3, 4, 2 minus minus 2, 4, and 2 minus 7 minus 5. And then the norm of this vector is going to be root negative 1 squared 1 plus 4 squared 16 plus 4 squared another 16 plus negative 5 squared 25 Then I have to add them all up. I get 32, 33 plus 25, 58. So root 58 would be the distance between these 2 points in R4. Okay, now the next thing we're going to define is the angle between the 2 vectors. And you can easily visualize that if you have 2 vectors in R2 or R3, there is an angle between these 2 vectors. There are actually 2 angles. So if you bring them to one point, let's say this is U and this is V, there is this angle, theta, and there is also this other angle, yes, which is going to be automatically 360 minus theta. We define the angle to be the smaller one. So the angle between U and V in R2 or R3 is the one determined by these 2 vectors that is between 0 and pi, that is between 0 and 180. So it could be an acute angle like this. The 2 vectors could be perpendicular. So you can have 2 vectors that are perpendicular like this. They make a 90-degree angle. They're said to be perpendicular or orthogonal. You can have 2 vectors like this, and these 2 vectors, they create an obtuse angle. The angle is greater than 90 but less than 180. And if you have 2 vectors that are pointing exactly towards opposite directions, then the angle is 180 or pi. Can never be more than that. Because the moment it's a little more, then the other angle, which is less than 180, is going to be the angle between the 2. And of course, if you have 2 vectors that point towards the same direction, then the angle between them would be 0. So if you have 2 vectors so that the angle between them is either 0 or 180, in both cases, they are parallel. If the angle is 0, they're pointing towards the same direction. If the angle is 180, they're pointing to the opposite directions. And the product, the dot product, or also called the Euclidean inner product, is defined based on the angle of the 2 vectors. So if you have 2 vectors, U and V, then U dot V, which is the dot product of U and V, is defined to be norm of U times norm of V times the cosine of the angle between them. And that's the case if U and V are non-zero vectors. So if U and V are non-zero vectors. If these 2 vectors, if at least one of them is 0, then you cannot find theta. Yes, because a 0 vector does not have any direction. So in that case, we define the dot product to be 0. So the dot product would be 0 if any of these 2 or both is 0. But you may also argue that this part is unnecessary, because if you have U dot V, norm of U times norm of V times cosine of theta, then if at least one of these 2 is 0, that is, if you're dealing with a 0 vector, then automatically this is going to be 0, because 0 times anything would be 0. This is just trying to be very rigorous and very specific. You can just think of this as the definition. Now, if I just divide both sides of this equation by norm of U times norm of V, I get this. Cosine of theta is U dot V over norm of U times norm of V. And also I noticed that since the denominator is always positive, because norm is a length cannot be negative. So norm of U times norm of V, the denominator here is always going to be positive. So I can see that if U dot V is positive, then cos theta is going to be positive. And if u dot v is 0, then automatically cos theta is going to be 0. And if u dot v is negative, then that would be equivalent to cos theta is negative. Okay. Now, what does this tell us? How can this observation help? So I'm going to remind you of the unit circle. If you have a unit circle, then you know that any angle could be put in the standard position like this, where the initial side of the angle is alongside the x-axis, the vertex of the angle is at the origin, and the terminal side of the angle will intersect with the unit circle at a point, and the coordinates of that point is going to be cos theta sine theta. So we learned that in trigonometry. So then from this, you can see that wherever x is positive, cosine is positive, and wherever y is positive, cosine is positive, and vice versa. So for example, if I'm talking about cosine of theta, since cosine is the x-axis, is the x coordinate of this point, it's going to be positive here and here, it's going to be negative here and here. And for example, if I'm talking about sine of theta, since sine theta is the y coordinate, then it's going to be positive in these two quadrants and negative in these two other quadrants. So now, if cosine is positive, yes, if the dot product is positive, then cosine is positive. And if cosine is positive, it means that the angle is going to be here in the first quadrant. Yes, because cosine is positive in the first quadrant. That means if the dot product is positive, then the cosine is positive, then the angle between two vectors is acute. It's less than 90 degrees, yes? First quadrant, between 0 and 90 degrees. And if you think of this point here on the unit circle, that's the point 0, 1. So we know that cosine of pi over 2 or 90 degrees is 0, because this point also corresponds to 90 degrees. Yes. So if the dot product between two vectors is 0, then that means cosine of the angle between the two vectors is 0. That means those two vectors are orthogonal. So they make a 90-degree angle between them. And if the dot product is positive, then the cosine, sorry, if dot product is negative, then the cosine of the angle between them is negative. And then that means we are here in the second quadrant, because in the second quadrant, cosine is negative. So that would mean that the two vectors, they create an obtuse angle. So that's the reason we have this. If theta is acute, theta is acute if and only if the dot product is positive. Theta is exactly 90 degrees, or pi over 2, if and only if the dot product is 0. And theta would be obtuse, meaning it's greater than 90, if and only if the dot product is negative. Any questions? So just by calculating the dot product, and later on we're going to learn a method of calculating the dot product by using the components. So we won't be using this formula very often to calculate the dot product. We will be using the components. And you'll see it's going to be very easy to calculate the dot product. And then just by looking at that, you can tell whether the two vectors form an obtuse angle, an acute angle, or a 90-degree angle. And also, you will be able to calculate the exact angle using this formula. But before that, let's take a look at some examples where we're using the formula that we just introduced to find the dot product. Any questions so far? So calculate the dot product of these two vectors, the vectors u0, 0, 1, which is k, and the vector v is 0, 2, 2. So if you graph these two vectors, you can see that the vectors, so this is the x, y, z coordinate system. So this vector here is 0, 0, 1. And then this vector here is going to lie in the yz plane. It's going to be like this. So for these two vectors, it's very easy to see that the angle between these two vectors is exactly 45 degrees. Because, as I said, the first vector is the standard unit vector k, and the other vector is a vector that lies in the plane of these two axes, which is the y-axis and the z-axis. And it's going to be right in the middle, so the angle between the two vectors is going to be 45 degrees. So in this case, it's very easy. Just find the norm of this one. Norm of u is 1. What's norm of v? It's going to be root 0 squared plus 2 squared plus 2 squared. That's root 8. So u dot v is going to be 1 times root 8 times cosine of pi over 4, which is 1 times root 8 times cosine of pi over 4 is root 2 over 2. So it's going to be root 16 over 2. So it's 4 over 2. It's 2. But, generally, if I just give you two vectors, you wouldn't be able to find the angle like that. So as I said, this is just an exception, and we're trying to practice this formula that we defined here. So in most cases, we cannot know the exact value of theta, and thus we need another method to calculate u and v, a method that is just basically on depend on the components, so that if you just know the components, you will see the answer. You will be able to do the operation. We can use the law of cosines to derive another formula for u dot v in terms of the vector components. So I'm going to remind you of the law of cosines. If you have for any triangle ABC, this is the general naming convention of a triangle. So A, B, C, and then the side across from A is lowercase a, the side across from C is lowercase c, the side across from B is lowercase b, and then we have the law of cosines. So for example, c squared is going to be a squared plus b squared minus 2ab cosine of c. Or a squared is going to be b squared plus c squared minus 2bc cosine of the angle A. And b squared is going to be a squared plus c squared minus 2ac cosine of the angle B. So this is called the law of cosine. So here I've written the formula for b squared. B squared is a squared plus c squared minus 2ac cosine of this angle here is the angle B, theta. Now, if I have two vectors u and v, then this vector here that goes from the end of v to the end of u is going to be u minus v. Because now we can see by the tip to tail method, if I add up v and u minus v, I get u. So if I just apply the law of cosines, if I take this one to be like a here, if I take this one to be like c here, and if I take the angle theta to be the angle b, and I use this last one, I'll get, so I can replace b squared with the norm of u minus v squared. I can replace a squared with the norm of u squared. I can replace c squared with the norm of v squared minus 2 norm of u, norm of v, cosine of the theta. However, you can now see that this part here, norm of u times norm of v times cos theta, is the dot product. So I can now isolate the dot product. So if I move the, so this is what I get norm of u minus v squared is norm of u squared plus norm of v squared minus 2 u dot v. Now, if I just move this to the left, move that to the right, I get 2u dot v is norm of u squared plus norm of v squared minus norm of u minus v squared. And then divide both sides by 2. So times this by 1 over 2. They cancel out. And here I get over 2. I get this. Now the rest is just simple algebra. I found the formula for u dot v. I already found the formula for u dot v that I can calculate just using the components. But if I simplify this formula more, for example, for R3, I can see if I replace norm of u squared with its value, norm of v squared with its value, and norm of u minus v squared with its value, and simplify, I get this very simple formula. If u is u1, u2, u3, and v is v1, v2, v3, I want to find u dot v, I would just have to multiply the corresponding components and then add them up. So it's going to be u1, v1, u2, v2, u3, v3, and then I add them up. That would be the dot product. So if we go back to the previous example, we had to think of the angle between u and v, and we found the angle to be 45 degrees, and we calculated the dot product, we found it to be 2. However, if we use this formula, we would get the same answer much more quickly. So u dot v is 0 times 0, 0, plus 0 times 2, that's 0, so 0 plus 0, 0, plus 1 times 2. So it's going to be 0 plus 0 plus 2. The answer is going to be 2. So as you can see, this formula is much easier to use. Is that clear? So this is something that we can prove in R2 and R3, because we can visualize R2 and R3. We can create, from using U and V, we can create a triangle in R2 and R3. And in both spaces, we will see that that's the case. So for example, if these are vectors from R2, U is going to be, let's say, U1, U2, and V is V1, V2, then U dot V is going to be U1, V1 plus U2, V2. Inspired by this, we're going to define the dot product for Rn to be like this. If U is this vector from Rn, and V is this vector from Rn, then the dot product of these two vectors is going to be, as you can see, the sum of the products that come from multiplying the corresponding components together. So u1 v1 plus u2 v2 all the way to un vn. Now I can use this in order to find the angle between two vectors. So we just learned that cos theta is going to be u dot v over norm of u norm of v. So if I have the vectors u 1 2 3 and the vector v negative 1 0 4, then cos theta, cosine of the angle between u and v, is going to be the product of these two, the dot product, which is going to be, let's see, negative 1 times 1, negative 1, plus 2 times 0 is 0, plus 3 times 4 is 12. And then at the bottom, I have norm of u, which is going to be root 1 squared plus 2 squared plus 3 squared. That's 9 plus 1, 10 plus 2, 4, 14. Norm of this one is going to be root 1 squared plus 0 squared plus 4 squared. That's going to be 16, 17. So it's going to be 11 over root 14 times root 17. Now, how do I get theta? I need a calculator for that. So theta is going to be cosine inverse of 11 over root 14 times root 17. So I want all of you to grab your calculator and do this with me. There is a second function cosine, which is the cos inverse. So second function cos, and then you open a brace. 11 divided by, then you open another brace, root 14 times root 17. You close the brace, and you close the brace again. And it will give you, you have to, okay, I forgot something. You have to put your calculator in degree mode. If you want to get this answer, you have to put your calculator in degree mode. So put your does everyone know how to put the calculator in degree mode? Yes, no? Okay. Everybody put your calculator in degree mode, and then you have to do second function cosine. So it gives you cos inverse, and then you open a brace. 11 divided by, you open another brace, root 14 times root 17, close the brace, and you hit equality. And you should all get this, 44.52 degrees. And you would get that if you first put your calculator in degree mode. Let's try that again. Get 44.5185. If you round that to the nearest hundredth, you get 44.52. Any questions? Okay, so let's take a look at the next example. Imagine you have a cube. This cube could be of any side. The side is k. So the length, the width, and the height is going to be k. Find the angle between the diagonal of this cube and one of its sides. So that it doesn't matter which side you pick, since it's totally symmetric, it's going to be the same. So you want to find the angle between the diagonal of the cube and one of the sides of the cube. So we can use what we learned about the dot product and this formula. To solve this problem. If we put that cube in at the origin of the XYZ coordinate system, then the diagonal of that, if each side is k, then the diagonal is going to be the vector that goes from the origin to the point k, k, k. So that diagonal as a vector is going to be the vector, let's say u, k, k, k. And we can pick any of the sides. So you can pick the side that's along the x-axis, or you can pick the side that's along the y-axis, or the one that's along the z-axis, doesn't matter. So the side that goes along the x-axis, I'm going to call that vector v, is going to be k, 0, 0. So we just then need to find the angle between these two vectors. So I'm going to give you a few minutes to try to get the answer. The answer is already here, but I want you to try this first. And you will see that it doesn't matter what k is, because it's going to cancel out from the numerator and the denominator. So just a couple minutes to work on this. Okay, so norm of v is easy to get. It's k squared plus 0 squared plus 0 squared square rooted. So it's going to be square root of k squared. It's going to be simply k, because k is positive. It's the length, so it's positive. Norm of u is going to be square root of k squared plus k squared plus k squared. So that's actually 3k squared. So that one is going to be k times root 3. What about u dot v? If I multiply these two and these two and these two and add them up, I'm going to get k squared. So theta, which is cos inverse of u dot v over norm of u times norm of v, is going to be cos inverse of, on top I have k squared, at the bottom I have the product of these two, that's k squared times root 3. So you can see that the k squared cancels k squared. It's going to be cos inverse of 1 over root 3. I'm going to just put my calculator in degree mode and then do second function cosine. That's cos inverse, open brace, 1 divided by root 3. Close the brace, equal, gives me 54.7356. Again, if I round it to the nearest hundredth, I get 54.74. Almost equal 54.74. So you all got the answer? Any questions?
No, it's good.
Very good. So here we have a very simple theorem about the relationship between norm and dot product. So if you multiply a vector v by itself, you're going to get norm of v squared, because imagine v is v1, v2, v3, a vector from 3 space. So if I want to multiply v by v, I'm going to get v1 squared plus v2 squared plus v3 squared. If you look at norm of v is the square root of v1 squared plus v2 squared plus v3 squared. So you can see that this here is actually norm of v squared. If I just raise this to the power of 2, I get the product of v and itself. So if I have norm of v, and if I have norm of v, I can write that as square root of v times v, because again, since norm of v squared is v dot v, if I take square root on both sides, I get norm of v equals square root of v dot v. So whenever you see in the problems, whenever you see norm of u, you can replace that with square root of u dot u. Or if you see norm of u squared, you can replace that with u dot u. And it will help doing the calculations because of the properties that we're going to learn about next. Okay, example 7, find k such that the angle between the vector u and v is pi over 6. So we have a vector u, root 3, 1, and we have a vector v, 1k, and we want to find k such that theta is exactly pi over 6. Okay, so we know that cosine of pi over 6 is root 3 over 2. And we also know that cosine of that angle, theta, is going to be u dot v over norm of u times norm of v. And we want to be cosine of pi over 6. So if I multiply these two using the dot product, I'm going to get 1 times root 3, that's root 3, plus k times 1k. That's what I get in the numerator. And then norm of u is going to be this squared plus this squared. So it's going to be root 4. And norm of v is going to be 1 squared plus k squared. And I want that to be cosine of pi over 6, which is root 3 over 2. So this is basically an equation. It's going to be a quadratic equation to solve. If I raise both sides of this to the power of 2, on this side I get 3 over 4. And if I raise this to the power of 2, I'm going to get 3 plus 2 times this. I'm using a plus b squared is a squared plus 2ab plus b squared. So it's going to be 2 times this. That's 2 root 3k plus k squared. At the bottom, if I raise this to the power of 2, I get 4. Raise this to the power of 2, I get 1 plus k squared. So I have this, which is a quadratic equation to solve. So I did the rest here. I could just simplify the bottoms. I have 4, and then I do cross multiplication. I get 3 times 1 plus k. So 3 times 1 plus k is equal 1 times this expression here. I get this. 3 times 1, 3. 3 times k squared is 3k squared. I move everything to one side because it's a quadratic equation, and it becomes this. Yes, and then from here on, I can use the quadratic formula to solve. So I have 2k squared minus 2 root 3k is equal to 0. This actually doesn't need the quadratic formula because it can be done by factoring. If I just factor out k, I get 2k minus 2 root 3 is equal to 0. So k is either 0 or k is root 3. So is this clear, or do you want me to explain this again?
I didn't get the last part.
Pardon me? The last part?
I didn't get, yeah, the last part.
This part that I put here?
Yeah.
Okay. So here, since I have k squared and k, I can factor out 1k. If I factor out 1k, I get 2k minus 2 root 3. So then I'm using something called the zero factor property. It's either k, this factor is 0, or this factor within the brackets, that's 0. So if 2k minus 2 root 3 is 0, then 2k is 2 root 3. That means k is root 3. You good?
Yeah, I get it. Thanks.
Sure. Next, we're going to look at some of the properties of dot product. Theorem: if u, v, and w are vectors in Rn, and k is a scalar. So u, v, and w, these are vectors from any space, and k is a scalar. Then, and all these properties, they come directly from the definition of the dot product. U dot v is going to be equal v dot u. So the dot product is commutative. And then we have u dot v plus w is going to be u dot v plus u dot w. So it's distributive. K times u dot v, and u dot v is a real number, so k times a real number is going to be a real number. It's the same as ku dot v, because you agree that ku would be a vector. So you can multiply a vector and another vector using dot product. So it doesn't matter whether you do the dot product first and then multiply by k, or you multiply k by u, for example, and then do the dot product. It's going to give you the same answer. And if you have any vector and you multiply it by itself, since this is going to be the same as norm of v squared, it's going to be greater than or equal to 0. And also we have this one. If the dot product of v and v is 0, then it automatically means that norm of v squared is 0. Then it means norm of v is 0. Then it would be equivalent to v is the 0 vector. Some more properties of the dot product. The same story if u, v, and w are vectors in Rn and k is a scalar. If you multiply the 0 vector and any vector v, you're going to get 0. So if you have 0, 0, 0, for example, and you have another vector v1, v2, v3, this is the 0 vector and this is v, and you multiply the 0 vector and v using the dot product, you're going to get 0 times v1, 0, plus 0 times v2, 0, plus 0 times v3, 0. That's going to be 0. Part B is just like part B here, except for w is on the other side. So again, you can also distribute from the right. This is going to be u times w plus v times w. This is again distributive property, but with minus. U times v minus w is uv minus uw. From the right, same story. U minus v times w is going to be u times w minus v times w. And what we have here is very similar to part C over here. You can also multiply k by v first. So if you have k times u dot v, that would be the same as u dot kv. So if you multiply k and v first and then do the dot product, it will give you the same answer as if you do the dot product first and multiply the result by k. So these properties, they allow us to do some algebra with the dot product. For example, if I want to simplify something like this, u minus 2v, which is a vector, times another vector, 3u plus 4v, I can use those distributive properties. I'm going to get 3u dot u, this times this, and then this times this. That's going to give me plus 4u dot v plus, if I multiply this times this, I get actually minus 6v dot u, and then this times this, minus 8v dot v. But this is equal to, I know u dot u is norm of u squared, so 3 norm of u squared. And when I look at these two, u dot v and v dot u are the same thing, because we have the commutative property. U dot v is equal to v dot u. So I get 4 of this minus 6 of this. That's going to be minus 2 u dot v, or I can write v dot u, it doesn't matter, minus 8 norm of v squared. So whatever I did here is just some algebra, and I went from this expression here into this expression. So the next example is interesting. If I have the product, if I have norm of u and norm of v and norm of the difference between u and v, I should be able to find u dot v. So we know norm of u is 3. Norm of v is 4. Norm of u minus v is given to be 5. The question is, what is u dot v? So the way to approach this is like this. You say u minus v, norm of u minus v squared is going to be u minus v dot product itself. It's going to be u minus v times u minus v. Then you're going to use those properties. The distributive properties gives you u dot u minus u dot v minus v dot u plus v dot v, which is going to be norm of u squared minus 2 u dot v, because these two are the same, plus norm of v squared. Now, since I have everything here, I can just plug in and get the value, yes? So 25, which is norm of u minus v squared, is equal norm of u squared, which is going to be 9, minus 2u dot v plus norm of v squared, it's going to be 16. So now I can isolate u dot v. In general, you get this formula. So if you isolate u dot v, you get 1 over 2 norm of u squared plus norm of v squared minus norm of u minus v squared. Okay, I'm going to cover one last thing, and then for the rest of it, I'll cover another day. The Cauchy-Schwarz inequality, which we're not proving, but it simply says that u dot v over norm of u times norm of v is something that's always between -1 and 1. And how this helps? It helps in defining the angle between any two vectors in Rn. So using this, we're going to define theta to be cos inverse of u dot v over norm of u times norm of v. And this theorem, the Cauchy-Schwarz theorem, it guarantees that this expression makes sense, because you cannot enter any value greater than 1 or any value greater than -1 into cos inverse. If you try, for example, to calculate cos inverse of 1.5 or cos inverse of -2 with your calculator, you get error. So the domain of this function is from -1 to 1. So the Cauchy-Schwarz theorem guarantees that this formula here makes sense. That is, what I have inside brackets here is never less than -1, and it's never greater than 1. So we can use this to be the angle between two vectors. So let's just give you one example how we can use this. I'm going to give you two vectors from R4, and we'll try to find the angle between these two. Even though we cannot visualize R4, we can define an angle between these two vectors and calculate that angle. So let's say we have the vector v 0, 1, 2, -1, and the vector u 2, 5, 1, 3, and we want to find the angle between these two vectors using this formula here. So what we need is first norm of u and v. So norm of v is going to be root 0 squared plus 1 squared plus 2 squared plus -1 squared. That's going to be 1 plus 4 plus 1. That's going to be root 6. And then for the other one, root u, that's going to be, I'm going to use my calculator for that one. 2 squared, that's 4, plus 25 squared, 5 squared, 25, plus 1, plus 9, it's going to be root 39. U dot v is going to be 0 times 2, 2, plus 1 times 5, 5, plus 2 times 1, 2, plus -1 times 3, that's negative 3. That is going to be 9 minus 3, 6. So theta is going to be cos inverse of 6 over root 6 times root 39. And this is going to be defined because what I have inside the brackets here is going to be between negative 1 and 1. I already know that the angle is going to be acute because the dot product is a positive number. So let's try to do that. Cos inverse of
Sir?
Yes?
When you did the u times v, 0 times 2 is 0, not 2.
Oh.
Because you did
yeah, you're
0
right.
times,
You're
yeah,
right,
okay.
you're right. So 0 times 2, that's 0. And then the next one is 5, the next one is 2, the next one is negative 3. Okay, so this is going to be 7 minus 3, 4. Okay, thank you very much. So 4 is also positive, so definitely the angle is going to be acute. Cos inverse of 4 divided by open brace root 6 times root 39, close the brace equal. I'm going to get 74.84 degrees. Okay, so I'm gonna stop the lecture here. How much